So this is Thermodynamics and Equilibrium Part 2. And so we're basically continuing our thought of all the different variables in basically the idea of thermodynamics. So this next concept is called the free energy concept. And if you remember back to video number 1, we said that if delta H minus T delta S is less than 0, we predict spontaneous. If it is greater than 0, we predict non-spontaneous. If it's equal to 0, we predict equilibrium. So, American physicist J. Willard Gibbs introduced this idea of free energy based upon these 3 rules. So basically he said, let's call delta H minus T delta S a value called delta G. And this is what we call free energy or Gibbs free energy. All right, so this is called Gibbs free energy. Okay, and we will often use it to predict spontaneity or non-spontaneity. Spontaneous. Oops. Jumped too far. So basically, Gibbs free energy, and just review, this is enthalpy. This is temperature in Kelvin. And this is entropy. Okay. And of course, we are at standard state. Remember, standard state is always indicated with these little degree symbols. So the standard state, we're saying 1 atm, 1 molar, 298 Kelvin. So in this particular case, and I would write this down on your periodic table. If delta G is less than minus 10, we say delta H is small, delta S is large, it is spontaneous, all right? The only way the Gibbs free energy value here could be negative or less than 10 is if this value, so if you're looking at it, okay, you're saying this is a large negative value, okay? The only way that happens is if this is small and then this is large, right? So then you get a large value here, and so it's negative, okay? If delta G, and this means spontaneous, okay? If delta H is large and delta S is small, let's look at it again. If you say this is positive, okay? The only way that happens is if your delta H is large, and then this number here is small, right? Because whatever you're subtracting has to be small for it to be a positive value, right? So this is non-spontaneous, okay? And when it's at equilibrium, we're predicting that delta G is between the values of plus 10 and minus 10. So we say it is at equilibrium, okay? Where delta S and delta H are fairly similar in terms of their values. So I would write this down somewhere on your periodic table so that you can always refer back to it. All right, so I'm going to walk you through some examples of how to calculate Gibbs free energy, and there are multiple ways of calculating this, so we're just going to walk through each of the ways. Despite if you use one way or the other, you're going to get the same answer. So when you're doing your homework, make sure you read the problem carefully because it will indicate to you clearly which method you need to use to solve for delta G. So one of the ways is to use the equation that we just talked about, where you have delta G is equal to delta H, or the enthalpy, minus the temperature times your delta S, okay? So I would just, look back on your table, and so again, either in your appendix or the back of your homework booklet or back of this chapter, chapter 18, you're going to have tables with delta H, S, and G. So you should have 3 tables. Okay. For this problem, you're going to need your H table, your enthalpy table, and your entropy table. Again, I would clearly mark each one, write it really big. Write delta H very big on top of the enthalpy table, and write delta S very big on top of the enthalpy table, so you don't use the wrong values from the wrong table. So really, how do you calculate it? If you're given an equation like nitrogen reacting with hydrogen gives you NH3 or ammonia, what you normally should do is you should find these values and write them down underneath. So if you're looking at the table, you're going to go 0, 0, minus 49.5. These are from the table. Okay. Okay. Then you're going to, of course, bring down your coefficients. Okay. And if you don't have a coefficient, you don't need to bring it down. And then you're going to look at your delta S. Again, these are from your table. Okay. And again, you should bring down your coefficients. Then remember, you're not doing the straight up sum, you're doing the products minus the reactants. Okay. So notice they've taken this value. I'm going to do it in color so you can see it. They're taking this value. Wow, it's so thick. Maybe thinner. They're taking this value. Wow. Okay, let's not do that. Let's just do pen. And let's do this. All right. They're taking this value here. And this is the product, minus the reactant, which is basically 0. So they have this, okay? And they get 91.8. Then they're going to take again the product and subtract it from the reactants. And again, it's the sum of the reactants, okay? So again, make sure you add them. It's the sum, okay? And so they get minus 190 joules per Kelvin, okay? Very, very important. Notice here, the units here are kilojoules. The units here are joules per Kelvin, okay? You cannot subtract kilojoules and joules. What they have done is they've converted everything to kilojoules. So if you have this value here, minus 198 joules per Kelvin, you need to convert from joules to kilojoules. And remember, kilojoules is the larger value, so 10 to the third or 1,000 in front of joules. This comes out to 0.1980 kilojoules per mole. Why? Because your joules have canceled out. So you are in kilojoules per K, not mole, sorry. Kilojoules per Kelvin. All right. So then we're taking this value here, we're bringing it down, okay? Delta H minus, so this is your delta H, minus T, and then this is your delta S. And again, your delta S is in kilojoules per Kelvin. Your Kelvin cancels out, so it's kilojoules minus kilojoules. So you end up with minus 32.8 kilojoules. It is very, very important that you remember to do this conversion on your homework. Otherwise, it will be incorrect. All right. This chapter, math is very straightforward. Really just remember that when you do the math, bring down your units. One of the easiest things to do, mistakes in this chapter, is to not have matching units when you're subtracting or adding. So Remember, you've got to either do kilojoules minus kilojoules or joules minus joules. All right. So they want you to calculate delta G for the following reaction, okay, and use the data given in the tables provided, okay. So basically, this is a straightforward, very similar to what you did before. You would solve for delta H, then you would solve for delta S, and then you would plug it in to solve for delta G, okay. So I don't really have space to do it here. Let's see, where can I do this? I'll just write in the values here. All right, so we're going to first solve for delta H. Okay, so we're doing products minus reactants. So remember, our products is CO2. So CO2 is minus 393.5. Okay, and our H2O is here, minus 241.8. Okay, and then we're going to subtract products. Oh, wait, hold on. Shouldn't write so small. Okay, there's 2 in front of H2O. So it is 2 times 2 minus 241.8. Hopefully you can see that. It's a minus 241.8. And then we're going to subtract CH4. CH4 is here. There's one of them, so minus 74.87 plus your 2 oxygens. And oxygen is 0. Okay. So this comes out to, and again, check my math. You can always, I'm just doing it real quickly. I get minus 15.23. Minus 15.23. And remember, I am in kilojoules per mole. All right. Then for delta S, let's write this down here so I can keep track. I've got my delta H. It's minus 15.23 kilojoules per mole. All right. I'm going to erase this calculation so I have space for the next calculation. Okay? Because I do need to figure out what is delta S. Okay? So we're looking at this next table here, and again we're looking for CO2, that's 213.7. And we have 2 of the waters. The water is 188.7. Oops. All right. Then we're going to subtract from that the reactants. CH4 is 186.1. And we have 2 oxygens, so 2 times 205.0. All right, so this comes out to, again, we pull out our handy dandy calculator. and I get -5. Let me just check that real quick. 213.7 times 2 times, plus 2 times 188.7, subtract 186.1 plus 2 times 180, 2 times 205. Yes, just confirming that, I get -5 joules per kmol. Okay, and remember, I'm subtracting these two values, so really what I need to do is I need to convert from joules to kilojoules. Okay, so this comes out to -0.005 kilojoules per kmol. All right, so let's write that down. Our delta S value is equal to -0.005 kilojoules per kmol. All right, having these two values in hand, now we're going to do the one last calculation to calculate delta G. All right, to calculate delta G, what we need to do is we need to go delta H, oops, typo there, delta G is equal to delta H, so minus 15.23 kilojoules per mole. Subtract the temperature is 298 because it is 25 degrees, times minus 0.005 kilojoules per kmol. Now, the kelvins cancel out, so we're both in kilojoules per mole, so we can do this math real quickly. Minus 15.23 minus 298 times minus 0.005. Okay, this comes out to minus 13.74 kilojoules per mole. So really, what I would do on the homework is I would do each one of these things separately. I would calculate delta H, and then delta S, and then plug it into my Gibbs free energy equation. All right. The other way to do this is really to calculate with the standard free energies of formation. So the third table that you have is a table of G values, or delta G Gibbs free energy values at standard state. Okay, so basically you're going to do the same thing. You're going to find the products, find the reactants, write the values down, and just do products minus reactants. So let's look at an example, 18.5. What you have there is C2H5OH reacting with oxygen to produce carbon dioxide and water. This is a combustion reaction. So again, what you're going to do is you're going to find these values. So let's do that right now. We're going to find, let's color coordinate it just, here we go. The ethanol is minus 174.9. And I do advise that you write it underneath when you're doing the homework. It really does help. Oxygen is 0. Carbon dioxide, oops. Let's color coordinate this here. Bring down the 2. Carbon dioxide is minus 394.4. And you have your 3 waters. And water is a gas here, not a liquid. So minus 228.6. All right. having those values in hand, again, really it is just take your products and you subtract your reactant values. Okay, so again, your delta G would equal 2 times minus 394.4 plus, it's a sum, 3 times minus 228.6. Okay, and then you're going to subtract the reactant, which is minus 174.9. Of course, you can add 0, but that won't do anything or won't change anything at all. So if you did this math, okay, it will come out to minus 1299.7. And from this table, if you're pulling these values, you are already in kilojoules per mole. Okay, because these values are in kilojoules per mole. And again, what I would do is I would pull this table from your homework booklet and write delta G very big in a box at the top so you know you're pulling from these values. Okay. Now, if you had used your other equation and you had used delta G equals delta H minus T delta S, will you have gotten the same answer as this? Absolutely. You would still get the same answer. And you should get the same answer. Okay? So again, when you're doing your homework, read it carefully. In some situations, they ask you to use the equation. In some situations, they ask you to do this kind of equation. So it just really depends. But either way, you should get the same answer. All right, let's do one more just to make sure we know how to do this. And again, it's just CaCO or calcium oxide. Again, we find it from the table. It is a solid, CaCO3 solid is right here, minus 1128.8. Okay, calcium oxide is right here. Oops, it didn't change colors. Hi, dear Lord. So it is minus 603.5. And your carbon dioxide is already shown here as minus 394.4. The stoichiometric coefficients in this case is 1, 1, and 1 because there's no numbers in front of these. So really, again, you're doing products minus reactants. So these are your products. This is your reactant. So basically, you're going to go delta G is equal to minus 603.5 plus minus 394.4. And then you're going to subtract the reactant. All right. And if you did this math all the way through, you're going to get 130.9, and we are in kilojoules per mole. All right, so hopefully you kind of have an idea of how to do all of these, both ways of calculating delta G or Gibbs free energy, okay? And the whole reason for calculating these values is to let us know whether something is spontaneous or not spontaneous. So let's look back. Okay, if delta G is negative, it is spontaneous. Delta G is positive or greater than 10, it is non-spontaneous. And if it's between the plus 10, minus 10, we predict equilibrium. All right. So basically, let's go back and look at some of these problems. Here, 130.9 is a greater than 10 situation, right? So that would be a situation of this, right? So really, this is what we call non-spontaneous, okay? Look at the problem before that, minus 1299.7. This is this first situation here, so we would say this is spontaneous. All right. We can look back even further. Oops. Okay. In this situation, we've got a minus 13. So again, minus 13 would be the first one. So we would say this is spontaneous. Okay. This would also be spontaneous because it's negative and less than negative 10. All right. So really, the whole idea is you calculate the Gibbs free energy and then you label the reaction as spontaneous, not spontaneous, or at equilibrium. All right. So I think I am going to stop here for video number 2, and we're going to continue with the next video and finish up this chapter with video number 3. So I would stop here, do the homework on calculating Gibbs free energy both ways, okay? And then once you do that, then watch the next video and then